Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alright, today we will continue on the Laplace transform. So basically, we have been introduced for what is Laplace transform. Okay, so how to find the inverse transform? Basically, we want to convert the xt to xs. Okay, how to convert this? We use a formula. We multiply the functions with e minus st. Okay, xt multiply with this one. Okay, so we can find the xt. We can find the xs, the functions in frequency domain. Okay, so today we will learn about pole and zero and also the regions of convergence. So poles and zero is actually the eigenfunctions of a system. Okay, so most of the time we will identify Hs by Ps over Qs, or in other words, we want to find the effects of the transfer function from the output divided by the input. Okay, so the poles are the roots of the denominator polynomial. So this is the denominator. Okay, so we want to know the roots of the polynomial. And the second one are the zeros, are the roots of the numerator. So this is the numerator. We want to know the roots of the polynomial. Okay, the value of the transfer function at some complex frequency is s equal to p. So it can also be identified as p, where this is the complex frequency. Some of the location is here. Okay, we have the real part and the imaginary part. Okay, and it can be also be identified as the exponential by ej phi. So we want to know, for example, this point, we have to identify what is the angle here, phi, and the equation is in exponential. Okay, alright, poles and zeros specify the set of complex frequency. So we want to know what is the eigenfunctions. Basically drawn at the S plane with x and zeros. Okay. Okay, so there can be more than one pole or zero at the same time, same location, especially when the higher order. So that means we have more than one values of the poles and zeros. Alright, so we can reconstruct Hs. Okay, so that means we can find what is Hs if we were given poles and zeros. So 0 and pole. So basically, if we see, we know that the numerator is s plus z and the denominator is s plus lambda I. So this is the value of 0 and pole. So we can know what is the transfer functions. Okay. So if there is multiply poles, okay, so this one, for example, s plus lambda I, this is s plus lambda 2 I, maybe 1, 2 until some numbers. So that means this is the numbers of order or order of the system. So the whatever how many the numbers of poles here, 1, 2 until what, so that is the order of the system. Okay, for example, we want to find the transfer function given by these equations, d squared yt over dt squared. That means this is the second order. plus 7 dyt over dt plus 12yt equivalent to dxt dt plus 2xt. Okay, so xt is the input and yt is the output. Okay, so we want to find the transfer functions. Hs usually is the output divided by the input. So now we have to solve these equations. So that's mean this is the second order. So s squared dot or multiply by ys plus 7s dot ys plus 12ys equivalent to, this is only 1, so s dot xs plus 2 dot xs. Okay, here is the first order, then this is the coefficient. Okay, so we factorize the ys and xs. So now we can divide ys divided by xs, output divided by input is equivalent to, we rearrange these two. So we got s plus 2 divided by s squared plus 7s plus 12. Alright, so now it is a transfer function. We factorize this one, become s plus 3 multiplied by s plus 4. So this is the denominator, which will known as poles. We'll know the poles, and this is the numerator. Okay, so at the top we got the eigenfunction as s equal to minus 2, and the poles s equal to minus 3 and minus 4. Okay, so now we want to plot the functions, zeros and poles at the s-plane. So s-plane means this is the real number and this is the imaginary part. So we know that poles are represented by x and zeros are by zeros. So 0, we know that minus 2, and the poles are at minus 3 and minus 4. So we just plot here. So now you already find the poles, zeros, and also the plot in s-plane. Okay. Now we learn about the region of convergence. Okay, so it also called the region of existence, means at which values the Laplace transform is exist. Okay, the region of convergence ROC is defined as the set of values of S. So we want to know the values of S at which the Laplace transform can be evaluated. Means we want to know from which area to which area that this integral will be evaluated. Okay, so there are several rules to be used to quickly determine ROC. That means we have to know the location of the poles and what type of signal is we are investigating. Okay, a pole is defined as the values of S that causes the denominator of the transform to become 0. Okay, so now we have to find what is the pole and the values the integral can be evaluated. So that is the region of convergence. Okay, so the convergent regions for this one, from, for example, from 0 to infinity, the function is e minus sigma t ft dt. Okay, so this is the functions, and then for the inverse Laplace is the fs. Okay, we inverse the fs, so we will find the ft by 1 over 2 pi j the functions multiplied by e minus st. Okay, so it related. Alright, so for the functions to be located at this one, just now it says that from 0 to infinity, that means it in this area. Okay, this is the region of convergence, and we identify what is the sigma. Okay, so from here we can know the region of convergence, and the values is located from the equations. Okay, So there are a few type of signals or region of convergence. So this region of convergence will follow the type of signals, whether it will be right-sided signals, start from somewhere here and ends at infinity, okay? Or it can be start from somewhere but it goes to the left, okay? So it will end at minus infinity. Or it can be from minus infinity to infinity. Or it can be bounded from somewhere here to somewhere here. It's called finite duration signal. So the rules of the region of convergence, okay, so it's usually to the left or to the right of a vertical line. So we have to identify what is the sigma and then we put a vertical line. Okay, if the xt is right-sided, then the ROC is right-sided. It will follow the signal. And if xt is left-sided, the ROC will be left-sided. Okay, and if the xt is two-sided, that means can be left or right, or the sum of left and right, then the ROC is either a strip, okay, so it can be strip, or else the individual ROC will not overlap. That means if we have a signal like this, okay, so when we identify the first one right-sided is here, okay, or it can be left-sided here, or for example this one, this two-sided, it can be this one and this one, okay, strip, or it will not overlap. That means there are two values of poles. Not overlap means one is to the right and one to the left, okay. And if xt is finite duration, then ROC is the entire S-plane, means it has it from minus infinity to infinity, okay. So this is right-sided, ROC also right-sided or left-sided, and then this is two-sided, okay, both positive here and here. Okay, for example, if we have a signal, this is E minus AT, okay, and then multiply by UT. Okay, for instance, we know that UT, that means is on the positive side, okay. So for the region of convergence, we will, for example, this is 1, okay, so we will just put values here, or more accurate is minus, okay, minus A, okay. So we just put the one vertical line, okay, and then it's a UT. That means the sigma is larger than the minus A. So we know that the region of convergence is at this side, okay, from minus A to infinity, okay. And for the second one, it's a minus EAT, okay. So it's something like this, okay, and then multiply by U minus T, okay. U minus T, that means we want to consider this side, okay, from 0 to infinity. So the region of the convergence, we know that the poles is here, minus A, okay, it's the values of the eigenfunctions, and then it's this side, so we draw a vertical line and the region of convergence is this side, okay. Alright, so the next one is how to find the inverse Laplace transform. Okay, so in principle, we know that just now I've shared, we just multiply the converted signal in frequency domain, multiply by E minus ST, and then we integrate from certain regions to a certain region and divided by what? 1 over 2j, multiply by 1 over 2 pi j or divided by 2 pi j. Okay, so we can use this formula, or rather we use the table. Okay, so if you want to using the table, we have to fractions or divided the a partial fraction expansion, okay, for the equation. So we know that these transfer functions, we can find the we can factorize and find the eigenfunctions. So first we will decompose the functions into simple terms using partial fraction expansion. Okay, so we know it can be factorized, and so it will be divided partially part by part. Okay, and then we will find the inverse of each term by find the matching entries in table 4.1. So what is table 4.1? If we can recall that we know that if a function is a delta t, the Laplace transform is 1. Okay, so we don't have to use the formula. That means we just we can compare the matching entries, whether it's a delta t to 1. But now we want to find from the xs to xt. Okay, previously we have saw this table, but we want to find the xt to xx. But now we want to find the inverse, so we can still use this table. So we identify what is the partial fraction, and then we find the matching entries. Okay, let's see one example. 3 over s minus 5 over s plus 1 plus 6 over 6 squared plus 4. Okay, so from the table, okay, we see from the table what is the function 1 over s. Okay, now 3 is the factor. So we put 3 outside and find the what is the Laplace from 1 over s. So 1 over s in the table is ut. Okay, so that means 3 multiplied by ut. Okay, and then the second one, okay, so the first one is 3 multiplied by ut. The second one is we will factor 5 outside as the coefficient or constant. So it will be 1 over s plus 1. Okay, so we'll find here 1 over s plus 1. So here we found 1. But here is negative. So the plus 1 will become minus 1. Okay, so the equivalent function is E. Okay, E lambda t ut. Okay, so again we have to use this one. So the plus 1 just now, if you match with the entry, is minus lambda. So now minus lambda means minus 1 here. Minus 1 equivalent to minus lambda in the equation. Okay, 5 is the factorized, so E minus t. And then again they have the ut. Okay, so it will just put it outside to be factorized again. And then we have 6 divided by s squared plus 4. Okay, so we find in the table which one. Okay, so this one is s squared plus b squared. Okay, so now we have to factorize 3 multiplied by 2 is 6 divided by s squared plus 2 squared. Okay, so it will looks like with the table. So now we identify the table as the lambda is 2. The b. Okay, the b is 2. And okay, so it's not this one, yeah, the second one, because the function just now is 2 divided by s squared plus 2 squared. So it looks alike with this one. Okay, so b is now 2. Okay, so sine 2t. 3 is the factorized from here. Okay, so ut will identify that this is from 0 to and larger than 0. Ut means all this function will be multiplied with ut. This is ut. Okay. Okay, second one, if we have s squared plus 12 divided by s multiplied by s plus 2 multiplied by s plus 3. So again, we have to make a partial fraction. A divided by s, b divided by s plus 2, and c s plus 3. Okay, so now the problem is we want to equate this and identify what is the A, B, and C. Okay, so for the first one, we want to find the coefficient for A. So we make S equivalent to 0. So we just take out S here, 1 over S, because we want to find A. So S squared plus 12 divided by S plus 2 multiplied by S plus 3. Find the function at S equal to 0. Okay, so you just substitute 0 and this one is 0. Okay, so A will become the 2. 12 divided by 3 multiplied by 2. Okay, the next one we have to find the B. So if you want to find the B, that means we take out the S plus 2 and then we know the equivalent eigenfunction is minus 2. So we substitute minus 2 to this function as minus 2. Okay, to find the value of B. Okay, so now B become minus 8. Okay, and then the next one C, so we take out S plus 3 and substitute S equivalent to minus 3 as the roots. Okay, and substitute here S minus 3, and now C is become 7. Okay, after this we can compare this value to the table. Okay, to the table, and then we can find the answer. Okay, so we will compare this value. A now become 2 divided by S plus S plus 2 plus C S plus 3. Okay, the value of B and C is minus 8 and 7. Okay, so obviously this is ut, and then this is E minus 2. Okay, this one is E 2t, and there is minus 8 here, and then plus 7 E minus 3t. Okay, so you can find the inverse Fourier transform. Alright, okay, so I will just stop until this example.